Does the function below have an inverse? All right, well, we're going to talk about inverses today, and we're going to answer this question as I just wrote. And how do you find the inverse? And why or not? Well, first off, when you talk about inverses have to be 1, 2, 1. What does that mean? Well, for every input, there's going to be one output. So every input, all right, every input, one output. Oops, you can't spell output, right? But also for every output, okay, there's going to be one input. And so a lot of times that means you need to pass the horizontal line test, the vertical line test, and also the horizontal line test. And so when you talk about a parabola like this is a function, so it passes the vertical line test. All right, so for every input, there is one output. However, for every output, there is more than one input, because at 1, we see that we have -1 and +1 for possible values. So this one does not have an inverse. However, all right, can we create a function that would have an inverse, all right, with this? Now, how will we go about doing that? Well, we know this doesn't have an inverse, but can we create one that would have an inverse? In order to do that, we need to isolate the domain. And so right here, what we can say is that we can actually take, and what happens if we use only half of this? So if we did this right here, we said, okay, I'm going to restrict the domain of this function to say where I'm only going to take only x values that are greater than or equal to 0. What then I have is a half of this, and so I get rid of this other part, and so now what we see is that yes, this type of function does pass the horizontal and vertical line test. So therefore, it is what we know as a one-to-one function. Boom, nailed it. So how do we find this inverse then? In order to find the inverse, we switch x and y's, as you probably know very well to do, and we would take the square root. And when you take the square root, you remember you bring a plus or a minus. However, in this case, okay, what we have here is going to be just the plus portion because we're using the positive values over there. And so what we know is that this function right here and this function right there are inverses of each other, because as we know that if we take this, we call this f, and let's just call this g. If I compose f composed of g, that will equal x, right? And so the square root of x squared does equal x, and therefore they are inverses of each other. Boom. Well, why are we talking about inverses here? Well, the reason why is because we want to talk about some trig functions and if they have inverses. Because we know the sine function right here is periodic and continues on forever and ever. Amen. Okay, so we have this, but the thing is that if this sine function 1, 2, 1? And the answer is no. No, because it is past the vertical line, the vertical line test, yeah, but it does not pass the horizontal line test because we hit many, many points there. Well, just like we did with x squared, we can restrict the domain of the sine function. So we can find an inverse. So how would we restrict this? Well, one thing we're going to do is we're going to try to get all the different values from -1. Okay, so this is -1 to 1. All right, all possible values from -1 to 1. And when we do this, if we actually take this sine function and we go right here, all right, so what is this right there? That would be from -pi/2 to this point right here, which is pi/2. If we restrict our domain of this sine function to all values between pi/2 and -pi/2, we would get the range of all possible ratios. And all those different possible ratios will give us angles. Now, not all of the angles, but as you can see, they would give us the angles, and as we know from negative pi over 2 to here, this would be in the fourth quadrant. And we would get all the angles and possibly in the first quadrant. And therefore, these would be good reference angles for every other function. And so what we know is that the inverse sine function, this means inverse, not reciprocal, the inverse sine function will have then, all right, the juxtaposition of the x's and y's. So over here, our outputs on this one are actually going to be the inputs over here. So as we input our ratios, so now that's going to be our x for this one, and this is our angles for here. We realize that, all right, when we plug in these different values, we can get, all right, the different sine functions. So when we have this right here, we have angle of negative pi over 2. That's going to give us a negative 1. We can see we get an angle of 0. All right, that's going to give us a value of 0. If we have an angle of pi over 2, we'll realize that it's going to give us a value of 1. Okay, and as we have this, we can see that, all right, if we change this up, we will have values from negative 1. All right, negative 1 is going to be negative pi over 2, which is roughly going to be like, I don't know, negative 1 point something. So I'll just put this right here. Oops, get a different color here, right there. And then as you can see right there, okay, we're going to go up to 0. And then somewhere right here at 1, okay, here's 1. And we're going to go a little bit farther than this, and we have that. And so what happens is that this is going to have some symmetry, and our graph is going to look like this. All right, and so that is what the inverse sine function looks like. All right, nice little symmetrical partner going through here. All right, along this y equals x line, another good indication of what we know about inverses. Okay, and so that's what we have there. Okay, so for our ratios, we know that the domain of inverse is going to be from negative 1 to 1, and the range is going to be all values between negative pi over 2 to pi over 2. The cosine, very, very similarly, all right, is where we would do this one. Well, this, unlike the sine, we're not going to start here at negative pi over 2 because we realize that this is actually where it does not pass the horizontal line test. And so what we're going to do is actually going to start here at 0. And we can travel all the way along here, all the way to this point, which we know is going to equal pi. And so what we realize is that if we restrict the cosine graph to all values from, all right, 0 to pi, all right, we now have a function that we have has an inverse. And so we can find this inverse, all right, not talking about inverse tangent here. Bring this down right there. Oopsie, sorry. Inverse cosine right there. Okay, and so we have for this inverse cosine graph, if we look at our table, all right, we're going to have our, okay, angles over here, which is now this. Our angles right there is going to be from 0. Okay, we have our pi over 2. We could probably put right there. And then we also have our pi. Okay, and this right here is going to be pi over 2. And so we have at 0, we're going to have a 1, and that's going to be our ratio. And our pi over 2 is going to be 0. And pi is going to be negative 1. So just like the sine graph, we have a domain then of negative 1 to 1. But unlike the sine graph, our range, all right, our range of our values goes from 0 to pi. And so when we graph this, all right, we can have, all right, negative 1 starting right here, and that's going to be a pi, and it's going to be way up here, okay, because that's a 3.14. We're going to have a 0, which is going to be pi over 2. All right, and that's going to be like somewhere right there. Okay, so like 1 point something right there, and then we have 1. Okay, or 1, which is right there, and it's going to be positive. What do we got here? 1 is going to be positive 0 right there. And I have to make sure I write this correctly because this should be, yeah, oh yeah, that's right. Okay. And so when we graph this, okay, once again, having some symmetry right there. And that's what we have. So as we draw this right here, we realize that this is symmetric over the y equals x line. And you can see its symmetric partners looking like that. So that green line is going to be our inverse cosine graph. And here's the table of values, obviously not in correct order, that we should know and love. Okay. And finally, what do we have for tangent? Well, good old tangent. Well, if we take one tangent here from negative pi over 2 to pi over 2, we realize that, yes, one of these tangent graphs actually gives us, all right, a perfect one-to-one function. So if we just restrict this value from negative pi over 2 to pi over 2, we'll have a one-to-one function we can use. Awesome. And so when we look at the inverse tangent, all right, once again, taking our x values over here, which we know are going to be our ratios. And if we know our outputs right here are going to be our angles. For this one, we can see that, all right, well, we know that in order to get this is that we have a value, we have actually an asymptote that is approaching. All right, so we have a horizontal, so this is a vertical asymptote. All right, vertical asymptote. Well, instead of a vertical, this is going to be a horizontal asymptote at negative pi over 2. And we have a horizontal asymptote. All right, this is going to be y equals that. And then we're going to have another one at pi over 2. And we see that this middle point right there, we're going to have a value at 0, 0. Okay, in the same way as we would have 1 and pi over 4. All right, oh, sorry, negative 1 and pi over negative pi over 4. And then right here, we could have pi over 4 and 1. And so when we graph this, okay, when we graph this, and I should make it blue just so we can graph it. All right, and so we have this right here at 1 point something, so we'll go like this, go la, 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 la. For our horizontal asymptote, I'll just say this is y equals pi over 2. All right, and we'll have negative 1 point something right here. All right, this is going to be y equals pi, negative pi over 2. We'll have 0, 0, which appears to be right there. And then at pi over 4, all right, pi over 4, which should be like there, and that'd be 1. And then we'll have negative pi over 4, which would be like right there, 1. And you have this graph that's going to kind of like this. And once again, you can see the symmetry coming through, y equaling x line of symmetry, and you can now see that that is what the tangent graph looks like. Both very, very weird, but very, very correct in that we have to restrict the domain of sine, cosine, and tangent in order to get the inverses. And that's why these graphs are a little bit different, okay? Just remember, when you find the inverse sine, it's going to be a restricted graph from negative outputs of negative pi over 2 to pi over 2 with inputs between negative 1 and 1. Okay, because those are our ratios. But we only get angle outputs either in the fourth quadrant or in the first quadrant. The cosine graph, once again, we have ratios putting in, all right, between negative 1 to 1. But we get angles, and this one's a little bit different, that are between 0 and pi, okay, which is basically between the, all right, first quadrant and goes into the second quadrant. All right, so that's why cosine, you get angles that could be 135 degrees if you put it in degrees, all right, or 120 degrees or anything between them. But you're not going to get anything that's going to be a negative angle, And then finally, tangent. Tangent, you can plug in really, because there's horizontal asymptotes, all right, our values for x are actually all real. So we can go from negative infinity, and I can't really put an equal sign there, all right, to infinity. All right, so it's all real. So I can plug any ratio in, all right, any ratio in from here. Okay, so any values right there, because we have a horizontal asymptote that keeps on going there. But we really then have, okay, values then, y values that are approaching negative pi over 2, and then also pi over 2, but never really get there. Okay, so we can't get 9 degrees or negative 9 degrees with the inverse tangent. All right, well, I hope this helps you out in understanding a little bit more about inverse trig functions and also why we need to restrict domains of inverse functions themselves. All right, good luck and God bless in the rest of your problems.